Hey, Algebra 2 Honor students, this is Unit 14, Day 3. Today we're going to extend some of your knowledge based on a prior homework of talking about the terms amplitude, frequency, and period. But before we do that, on Day 2, I kind of left you hanging a little bit, and I said, well, what about the graph of tan x? So in terms of the graph of tan x, to think about what tan x looks like, I'm going to base it off of what we've seen with the graphs of sine and cos. Okay, as a reminder, here's what the sine and cosine graphs look like. We were able to develop those based on what we saw with the unit circle. Well, for the graph of tan, what I'll have you recall is on the unit circle, tan is going to be equivalent to sine x over cosine x. So it turns out that if you take the values on the sine curve, those y values, and divide by the y values on the cosine curve, that's going to give you points that are on the tan curve. So let's take a look at what's happening right away at 0. If you do 0 divided by 1, that's going to be 0. So the first point that I'm going to plot on tan of x is, in fact, at 0, 0. All right, let's talk about what's happening at pi over 2. The sine curve, we're at 1. But on the cosine curve, we're at 0. So when I do 1 divided by 0 for tan, 1 over 0 is undefined. So when I have something that's undefined, graphically, that is representative of a vertical asymptote. So that's going to make tan look quite different than what we see for sine and cos. Moving over to pi, we're going to do 0 divided by -1 down here for cos. 0 over -1 is 0. And we're going to see a really kind of similar pattern repeat that at 3 pi over 2, you get -1 over 0. When 0 is on the bottom, it's undefined. But when 0 is in the numerator, we wind up getting 0. So far, that's really all we know about the graph, that it has these asymptotes at pi over 2 and 3 pi over 2, and it equals 0 at the other quadrantals. The last thing I'll kind of have you think about in order to generate the graph here is let's just look at what's happening in the first section from 0 to pi over 2. So what we notice is that the sine curve is positive and increasing. The cosine curve is positive, but it's decreasing. So if I think about the fact that it's this graph that I'm trying to generate is sine over cos, we have something that's increasing over something that's decreasing. So if the top of the fraction is getting bigger and the bottom of the fraction is getting smaller and smaller and smaller, the overall value of this fraction is getting quite large. And in fact, what happens is that that graph will approach infinity. And that's what graphs want to do when there's vertical asymptotes anyway. When you sketch a curve, okay, as it gets close to the asymptote, it's either going to go up to infinity or down to negative infinity. What winds up happening in the next section, just really quickly, is that sine is positive, but cosine goes below the x-axis. So when you do a positive over a negative, we know positive divided by negative is negative. So the tan curve is negative from pi over 2 to pi. Going to approach negative infinity as you get close to this vertical asymptote, but then as I curve around to the right, it's going to go through 0 at pi, and then maybe not surprisingly, from pi to 3 pi over 2, it's going to head up towards that vertical asymptote. Remember all-star trig class 2, tan is positive in 1, negative in quadrant 2, positive in 3, and then it would be negative in quadrant 4. So that's what the last piece of this graph would look like. And had I continued it on, just like the pattern for sine and cos, it would continue in that kind of like S-shaped-ish curved pattern forever and ever and ever. It would continue on the negative side like this. So here's what the graph of tan x looks like. Domain is a little bit more complicated to write here. You'd have to exclude all those asymptotes. But notice how the range is really nice. It's just negative infinity to infinity. All right, so there's a little bit about what the graph of tan x looks like. What we're now going to do is do our recap of what maybe you've saw in the homework with some graphing calculator activities and talk about functions of the form y equals a sine bx and y equals a cosine bx. And they share a lot of similar properties. Clearly, tan is kind of a whole different ballgame here, but a sine and a cosine of bx, they have a lot of the same properties. So that value out front, the value of a, is known as the amplitude. In fact, I want to define amplitude as the absolute value of a. Because sometimes there's a negative in front of this value, and that negative, we know, does some sort of transformation. But in general, the amplitude is always positive. And I want you to think of amplitude as being sort of the max height that the function takes on. So it's really the max height above the x-axis or above wherever the wrap line is. But that term wrap line will come later on in the unit, okay? So the height above the x-axis, the maximum value that we reach, that's going to be the value of the amplitude. All right, next we have something called the frequency. And the frequency is whatever the value of b is. How frequent is x occurring? And what you now know about the frequency based on the graphing calculator lab is that this is the number of cycles of the sine graph or cosine graph by the time you get to 360 degrees, which we'll probably just write as 2 pi. Right, 360 and 2 pi are the same thing. Typically, I label my axes in radians there. Okay. So then finally, if we know that the frequency is b, we're going to define something called the period. And the period represents how often one cycle occurs. Okay, so sine and cosine curves are called periodic functions. They occur over a certain period of time. Now, typically, it takes one sine or one cosine curve a span of 2 pi to finish its full cycle, right? So here's 2 pi, and then same thing. It takes 2 pi to finish the cycle. But if you change the frequency, if you take 2 pi and divide it by b, that would be the way we're going to define the period. This is how often we would see one cycle of the graph. Okay, so taking the total 2 pi and dividing it by the number of cycles that we have. That's how often we would see one. So we're going to use that information in order to graph some sine and cosine curves. As a reference point, you might want to have out page 15 from the notes where we graph the sine and cosine curve, because I'm going to base my two graphs off of what these look like right here. Okay, so for number 1, let's sketch the graph of y equals 3 sine 2x. And I'm going to give us the boundaries over what I want us to graph this over. Let's graph this from 0 to 2 pi. And maybe I'll change that up a little bit as we go throughout the lesson, but we'll try from 0 to 2 pi. All right, if you have graph paper for this lesson, by the way, that would be ideal so we can even be pretty accurate with our sketches. All right. I'm going to set up a set of axes here. All right, let's talk about some key pieces here. We know that the amplitude of this trig function is 3. We know that the frequency, the value of b is 2, which more importantly might tell us that the period is 2 pi over 2, which is pi. This is how often we're going to see one cycle of the sine graph. So if I label my axes right now, the amplitude of 3, that's the max height. So I'm going to put 3 up here on the y-axis. I also know that that implies that the lowest point is going to be at -3. And when we go from 0 to pi over 2, it's kind of up to you how you want to label the axes. I'm going to make every 2 spaces another pi over 2 here. I'll spread it out a little bit, but okay. So I want to graph it by the time I get to 2 pi. Here's what we're going to see. By the time I get to pi, this is not an asymptote, by the way. This is just a little border I'm drawing in. I have to see one cycle of sine finished by the time I get there. Well, I know what one cycle of sine looks like. It looks like this. It's a really rough sketch, but that's what I want to see by the time I get here. So I'm going to start at 0. I'm going to end at 0. And in the middle of the cycle, I'm at 0. In between the start and the middle, we have to be up at 3. In between the middle and the end, you got to be down at -3. So 3 sine 2x, here's that first cycle that you would see. And then you just hit repeat over here. By the end, I'm at 0. In the middle, I'm at 0. In between start and middle, up to 3. In between the middle and the end, down to -3. So here's how you should be able to sketch something like 3 sine 2x, even without the use of a graphing calculator. All right, so that one's not so bad. Let's take a look at something like y equals -2 cosine of 4x. And again, I'll sketch this from 0 to 2 pi. Okay. You know what? I don't really like my y-axis there. I'm gonna move this over a little bit. Sorry. Hopefully you're not too offended by that line there. Okay. I don't need any negative y value, negative x values, I should say. All right, so let's see. I'm going to put the x-axis there. That works. Okay, if I list some of the information for this one, the amplitude is 2. So be a little bit careful about that, that the amplitude we define as being absolute value of A. Now, with the negative out front, what that means is that this graph is going to get reflected over the x-axis. Normal cosine looks like this. So I have to now flip that over. Instead of looking like a valley, this one's going to look like a mountain. The frequency, the value of B, is 4, which means that the period is going to be 2 pi over 4, which is pi over 2. We need to see one cosine curve graphed by the time I get to pi over 2. That's really quick. Okay, let's see. I'm going to have to go up to 2 and down to -2 according to the amplitude. Let's see if I can kind of just spread this one out a little bit. I'm going to make, just because I know the period is pi over 2, I'm going to let every 4 spaces be pi over 2 for this one. So that's pi, 3 pi over 2. I think I'll fit it in here. 1, 2, 3, 4. Yeah, just squeeze it in. 2 pi. All right, by the time I get here, and again, this is not an asymptote, it's just kind of a boundary to keep myself started here. By the time I get there, I have to have completed 1 cycle of cos. Okay, the amplitude is 2. Oh, and by the way, because of that negative, it gets flipped over the x-axis. So we're not going to really see this. We're going to see this, upside down cos. So instead of starting up at the largest height, it's going to start down here at -2. It's going to end at that lowest point at -2. In the middle, it's up at the highest point. And in between the start and the middle, we go through 0. In between the middle and the end, go through 0. Okay. So there's my first cycle. That frequency of 4 tells you how many cycles you'll see by the time you get to 2 pi. So now, whatever you did in the first section from 0 to pi over 2, just hit repeat and keep going. So you're going to go to 0, 2, 0, and then by pi, you got to be down at -2 again. So there's that second cycle. All right, 0, 2, 0, -2. One more time. All right, 0, 2, 0, -2. And there we have it from 0 to 2 pi. That is what the graph of -2 cos 4x looks like. Let's do just one more. I'm going to change a couple things on you here. In this last example, let's graph maybe over a different interval that's not 0 to 2 pi. Let's do 2 sine, and I'm going to also change the frequency to 1/2. 2 sine of 1/2 x, and let's go this time from -pi to pi and see what that looks like. So if I'm equally spaced on my interval from -pi to pi, this is what I was starting to do before, but I didn't really want to do, is why don't we draw the y-axis this time right up and down the middle, because I want to go on the negative side and the positive side here. Okay. So when I go to make my sketch of 2 sine of 1/2 x from 0 to pi, just kind of spread things out a little bit. Let's make every 4 spaces that pi over 2 again, just like we had in the last example. You can choose whatever scale you want, but if you want to try and stay consistent with what I'm doing, go 4 spaces to the left. There's -pi over 2. I'll make this 2 and then this down here -2. And I know I'll need that for my max height according to the amplitude. Okay, amplitude is 2. Frequency this time is 1/2, which means that the period is 2 pi divided by 1/2. That looks weird. Dividing by 1/2 is like multiplying by 2. The period is 4 pi. Oh boy. So if it would take a total of 4 pi to see one cycle of the graph, we know the frequency of 1/2 means we would only see half the sine curve by the time I get to 2 pi. But I'm not even going to 2 pi. I'm only going to pi. Oh man. Here's what the normal sine curve looks like. This is what I would have seen by 2 pi if this is what I see by 4 pi. But I'm only going to pi. So hopefully you can see, guys, that you're just going to see this part of the graph. That's all you're going to see from 0 to pi. So sine still starts at 0. By the time you get to pi, it's just going to be a slow curve up to a height of 2. By the time you get to 2 pi, you'd be halfway done. We do need to go all the way out to 4 pi to finish that cycle out. So here's what this part of the graph would look like. Okay, and then on the left side, we don't do too much graphing on the left side, but it's going to repeat that pattern, okay? It's going to be kind of reflected through the origin right there. All right, so from here, instead of going up, we're going to go down, and by the time you be at pi, you'd be at -2. So the curve's going to look something like this. Now, again, if we were allowed to keep going and extend it out, it would eventually, on this side, come back up, and on this side, go down and hit the x-axis. It would follow that pattern, but it starts to look pretty weird when you change up the frequencies and then, of course, the interval over which we're graphing over. This is exactly what you would see if you went to your calculator right now, set your window to those values, and type that in as your equation. Talking about equations, that's the last part of today's lesson, is let's talk about writing equations. So what I mean by that is if I give you certain information, so for example, we're going to write the equation of a sine graph that has an amplitude of 5 and a period of pi over 6. If that's the given information, what would the equation of that sine graph look like? Okay. So we know that in general, we can write the equation as y equals a sine of bx, and we already know that a is 5. But to get the value of b is the frequency. It's not the period. When I'm given the period, the formula for period is 2 pi divided by b. So what we know is that 2 pi divided by b, in this example, is equal to pi over 6. So then just really quickly, you're going to go ahead and solve that for b. If you want to cross multiply, b times pi would equal 6 times 2 pi, which is 12 pi. Divide the pi out to get that the value of b is 12. So if a is 5 and b is 12, the equation would be y equals 5 sine of 12x. And there you have it. All right, let's do an equation with cos that's reflected over the x-axis with an amplitude of 10 and a period of 45 degrees. Oh man, I'm throwing a bunch at you here. So we're writing a cos equation. It got flipped over the x-axis. The amplitude is 10, period is 45 degrees. We know the end form has to be something of the form a cosine of bx. Luckily, we already know that amplitude. Let's talk about the period this time. The period's 45 degrees. So when I go to set up the formula for period, even though oftentimes we're going to be working with radians here, if this is in degrees, you have two options. You either have to convert to radians if you're going to use 2 pi over b, or 2 pi we know is the same thing as 360. So to find the value of b, if the period is given in degrees, just make sure you put that value on top in degrees as well. And then you can just as easily solve and figure out the value of b here. You would get 360 equals 45 times b. Oops, there has to be a 5 there. So therefore b in this one is equal to 8. When I go to write the equation, the last thing you have to pay attention to that we haven't referenced yet is that this one gets flipped over the x-axis. So when you flip over the x-axis, we know that the amplitude gets negated. So it's -10 cosine of 8x would be the equation. Okay. So once you get the hang of it, hopefully pretty straightforward there. Last thing that we'll do is, given some graphs, let's write the equation based on the graph there. Let's just do 2 of those. So I'll give you this graph right here to -2. Let's do that. Okay. So if you want to repeat this graph, I'm going to graph this for you. And then we'll sketch one more. Let's see. Let's do this. We'll call this value, let's do 2 pi down here. The interesting thing about these questions is that there are actually multiple acceptable answers. There's one that's probably easiest to come up with, but it doesn't mean that that's the only possible answer. Okay. If we take a look at number 3 just to get started, hopefully you're looking at that and thinking that this looks like a sine curve. So I'm going to try to write an equation with sine in it. The amplitude of this graph is 2. The period is how often we see that one cycle completed. So the period is going to be pi. And if the period is pi, what that tells me is the value of b, the frequency, is 2. If you see one cycle by pi, a second cycle gets completed by 2 pi. So the frequency is how many cycles by 2 pi. All right, so if b equals 2, the equation here would be y equals actually just 2 sine of 2x for number 3, based on the amplitude and the value of b for the frequency. Okay. And then finally here, if you're taking a look at number 4, this one's a little bit weird, but I would hopefully identify this one as being a cos equation. Sine always starts at the origin no matter what. So if it doesn't start at the origin, I would classify as being cos, but typically cos starts at the highest point. So maybe I'm going to say that this is a negative cosine equation. And I can see 1, 2, 3 that the amplitude is 3. But the question is, what's the frequency? Because I don't see one full upside down cosine curve yet, right? An upside down cos curve would look like that. So the period turns out that even though I'm only seeing half the graph, the period is 4 pi. But that key thing that I just said, as far as only seeing half the graph, that's the number that I need. The frequency is how many curves you see by 2 pi. I only see half of a cosine curve. Oh, and by the way, it's half of an upside down cos curve. So you don't always have to write the period. When we're writing the equation, you definitely need that value of b. If you have what's going on until 2 pi, that's maybe one of the best things to write down and identify. So this last equation here is the representative of y equals -3, negate the amplitude, cosine of 1/2 x. And I think with some more practice with these, you'll get to become an all-star at identifying trig equations. But there's definitely more transformations to come with sine and cos. I think that's probably good for today. If you have any questions, let me know next time I see you. Have a good one.